Assalamu alaikum. So today we are going to do free fall, and this is the setup we are going to use for our experiment. And this setup, uh, this setup is just used to find the time of fall of this ball. Imagine if I'm going to drop this ball, what will happen? The ball will fall, right? Yeah, we call this a free fall. Why we call it free fall? Because the only force acting on it is gravitational force. Because of that force, we know that force is mg, and the mass, okay, because of that force the object is accelerated. And what is the acceleration in this case? Yes, the acceleration is we call acceleration due to gravity, and it is we usually represent it by the letter g. We know that it is 9.8 meter per second square. So this is our experimental setup to determine acceleration due to gravity experimentally. I'm going to just explain you what we have here. You can see here, this is a switch. Actually, when the ball hit the switch, when the ball hit this, the switch will be click. That means it will be going for an off position. And here another switch I have. Here I am going to keep the ball here by pressing this. And this is a metal and this is a metal. Here this metal, these two metal comes in contact. It will behave like a switch. And you can see that this switch is connected to a timer here. And the moment I drop this, you can see that the moment I drop this, the stopwatch will start. You can see that the moment I drop, the switch is on and the timer is working. The moment it hit, the stopwatch stops, so that we will get the time, accurate time of the fall. That means imagine if I'm going to drop this object, we know that its initial velocity is 0. And of course, I have a setup like this. I have a meter scale so that I can measure the distance it traveled by using this adjustments. So if I know the distance it traveled and if I get the time, let me show you. If I drop it once again, you see the ball is going to start, and it took around 0.3712 seconds. That means fractions of seconds can be easily determined. So this setup we are going to use to determine the value of g. I'm going to show you how we are going to do it experimentally. I'm just going to explain it theoretically a little bit. And everybody know that. In this setup, what did you see? In this setup, if I drop an object from this point, let's say this point, and here I place the stopwatch. Here I place another switch. That means if I drop this, I can easily get the time for this object to fall all the way down here. That means the time of fall is known. And also we know the initial velocity because I said I'm going to drop it. And of course it's a case of free fall. So the only value of force is mg. So the acceleration is g. And by the help of this scale, we measure the distance d. So today, now I have few things. I know d, I know t, and I know initial velocity. Is these three is enough for me to calculate g experimentally? Yes, we learned already from these three informations how can we reach the acceleration due to gravity g. Okay, so that we can use the displacement time relation. Can you please remind me about the displacement time relation? Yes, the displacement in the y direction, if I call delta y, yes, delta y is equal to velocity, initial velocity in the y direction. Yeah, it is v initial y t plus half a. In the case here, a is g, half g t square. Of course, this is a well-known relation and you did it many times. So here in this equation, we know that the delta y is the distance traveled. So instead of delta y, if I place d and initial velocity, what is initial velocity in this case? 0, half gt square, right? So d is equal to half gt square. D is equal to half gt square. Or we can say d is proportional to t square. Why? Because g is a constant. That means d is equal to a constant into t square. Or mathematically we can write d is proportional to t square. So right now what is our plan? Our plan is to reduce the distance d. So I have a d value, and the corresponding t. But we understand d is proportional to t square. So that means mathematically, if I can calculate t square, it's fine, right? I have d and t square. One set of d and t square. What is my plan? I'm going to reduce this height to another 10 centimeter down. So the d is decreased. What will happen if I decrease the d? I have a second d. I decrease the d, of course, the distance it travel is less, so the time will be less. I will get another time. Of course, I can find time square. Now, I'm going to repeat this with a different d. So I will have a set of d and time square. And of course, we understand mathematically d is proportional to t square. Once we have these set of readings and we understand that d is proportional to t square, what we can do, as the way we did other experiments, we're going to plot a graph, and in which I'm going to plot d along the y-axis and t square along the x-axis. And what we learned, they are directly proportional, so that we will see that the data will be in a line. They are in one line, so that we will get a straight line. And once we have the straight line, the computer program is going to help us to plot this graph, and we can easily find the slope. What will be the slope? Slope is, this is the equation, right? d equal to half g t square. I plot this in the y-axis and t square in the x-axis. So the slope is y equal to mx, right? The slope is what? Half g. Or we can easily look into this, the slope, because we know that slope equal to what? Slope equal to delta y by delta x, right? What is delta y here? The y displacement. Delta y is d, and what is delta x? T square. D by t square, mathematically from this relation, what is d divided by t square? D divided by t square. D divided by t square is half g. Exactly, the slope represents half g. Now, after getting these readings, when we plot, we'll get a straight line, and from the straight line we can find the slope, and the slope will be equal to half g. Therefore, once we have the slope is equal to half g, therefore we can get g. What is g? 2 times slope. So we are going to find the experimental value of g, that is equal to 2 times slope. And that is our experimental plan, and we are going to do that here. We are going to take the first measurement. So I'm going to use this meter scale. You can see that here it is 10, 20, this all in centimeters, right? So you need to read it in centimeter. But when we are doing the calculation, we always measure them in meter. So you know that if it is 60 means 0.60, 60 means 0.6 meter, right? So let me check the height of this. If I keep this ball here, let me show you how to keep the ball. I'm going to take the ball here and going to bring it here and then press this spring the rod. Then I can keep it here by tightening the screw. So when I tighten the screw, it will stay there. So that now I'm going to make sure that I'm going to reset it so that the machine reads 0. Now I'm going to measure the height of this. I'm going to keep this meter scale on the top, and I will show, I'm going to read it. I'm going to read this where this pointer is. I believe I bring it very close to 60, so that the distance d is 60 centimeter, right? Now what I'm going to do, I'm going to drop the object. I'm going to drop the ball. Before I drop the ball, I'm going to recheck whether this is fine. This is in 0. This is, it is reset to 0. Now I'm going to drop it. So the moment I drop, this machine reads the displacement. The machine reads the time, and also we know the displacement, and the time it shows 0.3501 second in order to have a distance of d, and that's all.